In this class we are going to talk about reverse micellar extraction and aqueous two-phase extraction. Both involves water. As you know, biomolecules like proteins or enzymes, they can easily denature if you are using solvent, when you are using a solvent type of extraction. So, if you are using water, then those biomolecules will retain its activity, and that is where these type of reverse micellar and aqueous two-phase extraction techniques are very useful. That means the phases are only water, so there is no chances of those biomolecules getting denatured or degraded. So, let us first understand what is a surfactant. Okay, surfactant is a surface active agent, and it contains a hydrophobic tail. Okay, it could be long chain hydrocarbon, or sometimes it could be an aromatic group, and it will have a polar head group. It may have oxygen, nitrogen and so on. So, this portion will always like water, and this portion will like organic solvent. So, these surfactants or amphiphilic molecules, they are always found in the interface between water and any solvent. So, that is the advantage of this type of compounds which have a polar group and a long hydrophobic tail. So, there are large number of surfactants. There are surfactants which are neutral, there are anionic surfactants, cationic surfactants. So, surfactants have become part of our life, even your washing up liquid, your dishwasher, so your soap, everything contains this type of surface active agents. So, they can interface between an oil layer and a water layer. So, surfactants are used in reverse micellar type of extraction. So, how does it work? So, surfactants aggregate in organic solvents. Okay. So, suppose I put these in organic solvents, they will aggregate. So, all the polar groups will come together and form sort of a cavity, okay, and all the tails which are hydrophobic will be outside, and this happens especially at a concentration which is called critical micellar concentration, CMC. So, at lower concentration it is not enough to form aggregates, but around that concentration, critical micellar concentration, they form an aggregate. So, what happens is you get polar pockets, and the tails which are hydrophobic point outside. So, proteins or enzymes could be captured in these polar pockets, because water also will be present inside these polar pockets actually. So, the reverse micelle systems will contain some water inside as well as some hydrophilic solutes, like it can contain even biomolecules and so on. So, that way we can transport biomolecules without getting worried that they may get denatured in a hydrocarbon or a hydrophobic environments. That is what this is called a reverse micelle. So, what do? We have the organic solvent, all the surfactant aggregate, the polar groups all pointing inwards. So, inside you have a polar cavity. So, the protein and water will be captured inside actually, and this is what is called a reverse micellar phase, and this can act as an extracting solvent. So, it will have a polar core, that is what it is actually, a polar core. So, I can use different types of surfactants, surfactants which will form big hydrophilic cores, surfactants which will form small polar cores and so on actually. So, what do? So, I have the aqueous phase, I have the protein here, then I have the organic phase. So, I can have in the organic phase reverse micelles of surfactants, and the proteins are inside the reverse micelle, that is what happens. So, what are the factors that influence this partitioning and extraction of proteins from bulk aqueous phase into the reverse micellar organic solution? So, basically you need to know that the protein originally are in aqueous phase, and you have taken these proteins inside the organic phase. If I do not do it in a reverse micellar form, the proteins will get denatured because they have come into the organic phase. But having this type of reverse micelle, I am maintaining their aqueous environment inside this polar cavity. So, what are the factors that affect this? The pH, the ionic strength, type of salt I use, type of organic solvent I have, type of surfactant I use and so on actually. So, there will be a lot of non-bonded interaction between the protein and the surfactant polar head groups. It could be electrostatic, ionic. If the surfactant is ionic, it could be ionic forces and so on actually. These are the different types of forces that act. So, the solubility of protein at pH less than its isoelectric pH. So, you all know what is isoelectric pH, right? that is the pH at this where protein will not have any charge, okay, that is the isoelectric pH. But when the pH is less than the isoelectric pH, then the protein will have a positive charge. Now then it is greater in an anionic surfactant. So if you are working with the pH less than the isoelectric pH of the protein, protein will have a positive charge, so it is better to have a anionic surfactant. If the pH is greater than the isoelectric pH, okay, so then it will have a negative charge, then anionic surfactant would inhibit reverse micellar. Solubility of protein would be more at pH greater than the isoelectric pH. So if it is greater than isoelectric pH, then what happens, protein will have a net negative charge, okay, then it is good to have cationic surfactant. So depending upon the pH, whether I am operating below the isoelectric pH, okay, whether I am operating above the isoelectric pH. So if I am operating below the isoelectric pH, it is good to have anionic surfactant. If I am operating above, then it is better to use a cationic surfactant. So pH effect is seen here. Higher salt concentration, if I am using very high salt concentrations, they will screen the electrostatic interaction, so it will decrease protein solubilization. Higher ionic strengths results in the formation of small reverse micelles, and protein solubilization is reduced because of the size of these the polar pockets are very small. So protein will not go inside because of the size effect. So increased ionic strengths lead to salting out of the protein also from the micellar phase. Increase in surfactant concentration increases the formation of reverse micelle, hence it also increases the solubilization of protein. So I can have higher surfactant concentration, I can solubilize more protein. If I use higher salt, obviously I am going to end up having the salt sort of screening the interaction between the protein and the surfactant molecule, okay. But if I has too much ionic strength, there could be salting out of the protein from the micellar phase. So I can sort of balance between all these, the ionic strength, the salt concentration and the surfactant concentration. Reverse micelles formed by ionic surfactants are small, so it cannot accommodate larger proteins, whereas non-ionic surfactants can form large micelles, so we can have larger amount of proteins, okay. So if I have non-ionic surfactants, then I can have larger micelles, but then I may select ionic surfactants based on whether the protein has a net positive charge or negative charge, so that the capture of those proteins by the surfactant is also enhanced, okay. Then reverse micelle are thermodynamically stable and they are nano sized assemblies of surfactants. How do you re-extract? I can re-extract by adding fresh aqueous at a proper pH and proper high ionic strength, okay. They encapsulate small amount of water in bulk organic phase, okay. So because I need to again re-extract the entire protein which has been taken in using a reverse micelle system. So for example, I have surfactants like this, and then they are forming a core inside. We have the oil phase, the core is the polar core or the aqueous core. So the surfactant in organic phase, okay, so it gets taken in, and then later on we use mixer and centrifuge and so on, so that as much of the protein is captured inside actually. So water content of reverse micelle, we will say water divided by amount of surfactant. There is some term called aggregation number, okay. So this aggregation number is average molecular weight of reverse micelle divided molecular weight of the surfactant, okay. These are some numbers which you may have to remember. So 4 regions where reverse micelle will have the solutes of the protein, either bulk organic phase, interface of the surfactant head groups and the water pool in the reverse micelle, water pool inside the reverse micelle, excess aqueous phase. So all these places you may have the solute or the protein present actually. So how do you classify these surfactants? Anionic, cationic, non-ionic. So anionic, ammonium lauryl sulphate, SDS, sodium dodecyl sulfonate, AOT, DOLPA. Cationic, it could be CTAB, DTAB, TOMAC. Non-ionic, twin 85, TX100, phospholipids and so on. So we have 3 types, and generally with the anionic or cationic you have electrostatic forces, whereas non-ionic there is no electric charge. So, generally it is hydrophobic and hydrogen bond type of non-bonded. So, what are the solvents we use? We use isooctane, N-decane, cyclohexane, carbon tetrachloride. Sometimes you may also use small co-solvent like isopropanol, butanol, hexanol, octanol and so on actually. So, you can see the type of surfactants that are used and the type of solvents and co-solvents used actually. So, what are the factors that affect the protein solubility? The water content in reverse micelle, the type of organic phase, the type of aqueous phase and characteristics of the protein also comes into picture. So, organic phase if we take, we will say type of surfactant used, type of solvent used, any co-solvent used, surfactant concentration. If you take aqueous, what is the pH, type of salt used, what is the ionic strength. If you take the characteristics of protein, whether the protein is hydrophobic or hydrophilic, charge on the protein, molecular mass, that means how bulky it is, shape of the protein. So, all these affect. So, it involves two steps, one is the forward, other one is the backward, okay, backward, forward, backward. So, protein is transferred from the bulk aqueous phase into the micro water pool in the organic phase and then protein is taken back into the fresh aqueous phase, okay. So, what are the problems in back extraction? Because decrease in protein activity, because you have put in reverse micelle with surfactant, then again you are re-extracting into aqueous phase. So, the activity of the protein may lose. Use of non-ionic surfactants can increase the protein yield. The slow process, this is a very slow process, the backward reaction, because of the interfacial resistance to protein to get released. So, we can use high salt concentration, high pH, temperature, addition of counter ionic surfactant, destabilizing solvents, all these we can add. You have to be very careful that you do not reduce the activity of the protein which you have extracted originally, okay, that is very important. You can also have mixed reverse micelle to avoid protein deactivation in ionic reverse micelle. We can have slow back extraction rate and we can have strong, especially to overcome strong electrostatic interaction in ionic reverse micelle, okay. So, we can use non-ionic surfactants added to ionic reverse micelles for protein solubilization. This non-ionic could be twin AT, AOT and so on. Enhancement of enzymatic activity in mixed reverse micelle by adjustment of the microenvironment polarity, okay. So, that also can be done by adding non-ionic surfactants. Then there is something called affinity based reverse micelle. So, what we do is we add a affinity ligand so that the selectivity can be enhanced. That means there will be an affinity ligand in the which will specifically capture only the protein of our interest, okay, ligand protein interaction. So, we can separate proteins with higher selectivity and higher purification by adding an affinity ligand during the reverse micelle process actually. So, this is affinity based reverse micelle. So, this can be specific ligand specific for single compounds so that the protein, if it is antibody is available, it is very expensive. Group ligands, that is group specific interactions, binds to a range of similar compounds, okay. So, that is what it is. For example, metal chelating ligands for extraction of hemoglobin that acts as hydrophilic head of affinity cosurfactant, that is one idea, okay. So, ligand complex formation, then you have selective removal of the complex using reverse micelle, okay. Then back extraction in stripping solution and then you have to separate the ligand and the ligate, that is very important. So, initially we have the ligand ligate and they form the complex and then we go into this extraction process. This is the normal aqueous to phase extraction. Then we have the back extraction, okay. Then you have to separate the ligand and ligate. So, 4 steps are there, okay. But then you can get very pure protein of your interest from mixture of proteins by having the proper ligand which are very specific for that particular protein, that is the advantage. So, the binding constant for protein ligand complex determines the selectivity of the extraction. The stronger the binding of protein to the ligand, the lower the ligand concentration required for selective extraction. This is obvious. The selectivity increases exponentially with increasing the number of binding sites on the protein molecule. So, number of binding sites determine the yield. So, same ligand if it can bind on n sites, then your extraction efficiency also goes up by that factor, okay. Then let us come to something called aqueous two phase extraction, okay. So, and we looked at the reverse micelle aqueous two phase. Imagine we have a protein in one phase, I want to extract with another aqueous phase, that is very challenging, right. So, how do we do that? We have a polymer solution added to one of the phases, and we have the salt and the solute in one phase. So, the addition of polymer affects the partitioning of the protein from one phase to another. So, we can have different types of biopolymers. So, partition of solute between two water rich phases, distribution of biopolymer. So, it could be charge interaction, hydrogen bond, van der Waals between the solute molecules and polymer molecules. So, what determines the separation? Molecular weight of polymers, type and concentration of salt, pH and temperature. Okay. So, I can have different types of polymers like PEG or dextran or glucan in one phase, another phase where the solute is present contains salt. So, the solute partitions into the polymer phase. Okay. That is what happens in the aqueous two phase extraction. So, recovery of bulk protein and valuable proteins from waste stream, for example, alkaline protease from B, lichenophorm by aqueous two phase extraction using PEG. So, we are using PEG as your polymeric solution here. So, partitioning of cell debris, disruption of biomass, then you have the desired product, it will have viscous colloidal suspension, organelle, cell wall fragments and other. So, the separation of solids by conventional solid liquid separation is difficult, whereas we can achieve by contacting the cell homogenate with PEG and potassium phosphate extractant to partition the cell debris and particulates into the heavy raffinate. So, normally we used to say that after when you have the cell debris and cell wall fragments, we can do a centrifugation, or we can do a to remove cell debris or the solids, but sometimes it may become very difficult because of the viscosity. So, then we can use this type of two phase aqueous two phase extraction using PEG. So, all the cell debris and other particulate matter can go into that phase, leaving your desired product in the mother liquor. Okay. So, applications of aqueous two phase: recovery of enzymes, fumarase, penicillin acylase, formate dehydrogenase from fermentation broth, fumarase recovered from baker's yeast, homogenate, penicillin acylase from fermentation broth of recombinant E. coli. So, all these processes are carried out in aqueous two phase extraction type of method. So, the partition coefficient is expressed as function of 5 factors, electrical, hydrophobic effect, hydrophilic effect, conformational effect and ligand type interaction. So, that is how we calculate. And typical values for partition for cell fragments, DNA 100, for proteins and enzyme 10. So, what does that mean? So, if I have a PEG solution, cells and debris will partition preferentially rather than the proteins and the enzymes. Okay. So, the effect of polymer molecular weight on the partition coefficient is also there. If I am looking at extraction of fumarase from a protein mixture in PEG potassium phosphate system, fumarase extracted in the aqueous PEG phase, the K value increases with increasing PEG 400. Okay. So, if I put in more PEG 400, I am able to increase the extraction of PEG, whereas when I am increasing molecular weight of the polymer, it decreases the partitioning of the protein in that phase. Okay. So, if I increase molecular weight, the partition coefficient decreases. So, if I keep lower molecular weight, partition coefficient increases. Similar effect was observed with decreasing the partitioning of polyolanols in PEG phase of PEG dextran system. The K value decreased from 1.3 to 0.25 as the molecular weight of the polymer is increased from 1500 to 6000. So, at higher PEG molecular weight, the K values were not affected. So, at higher, but at certain range, as you increase the molecular weight of PEG, the K value keeps decreasing. So, what are the equipments for aqueous two phase? We can have batch or continuous mode. So, continuous extraction, better product uniformity and purity, automated operation, better control of partitioning conditions. It can be small process equipment when compared to batch. Batch I will require very large equipments. It is easier to integrate with other downstream process. Okay. So, when I have a continuous, it is easy to integrate. Otherwise, if it is a batch, I need a storage vessel where I keep the product, and then high viscosity of extract phase will affect the mass transfer kinetics and phase separation. As you know, high viscosity affects the diffusion coefficient, hence the mass transfer coefficient. Low interfacial tension in aqueous two phase system, which will facilitate emulsion formation, hindering phase separation. So, the equipments: inline static mixers with centrifugal separations, disc stack centrifuges, nozzle separators or decanter extractors, batch well as as well as continuous operations in all these actually. So, it is very good because it involves transfer of solute from one aqueous to another, as I said, immiscible aqueous phases, that is very important, the phases have to be immiscible. So, you may have polymer in one phase, salt in one phase, it will be immiscible, and it can be either be a polymer system or a polymer salt system. So, it is, as I said, it is very useful for biomolecules. Okay. So, it was very old, developed very long time back, but then it became very popular only recently because of large biomolecules which needs to be removed without losing its activity. The water content in aqueous systems is as high as 85 to 99. So, what type of polymer we used? Polyethylene glycol, dextran, polyethylene glycol, polylan, PEG, PVA, PEG, hydroxy propyl starch. If you look here for polymer salt, PEG phosphate, PEG citrate, PEG sulfate. So, these are very common. As you can see, PEG is very common, that is widely used because it is very hydrophilic and it does not affect the protein systems. So, there is something term called partition coefficient K, that is the concentration of the protein in the top phase, concentration of the protein in the bottom phase. So, if K is 1, protein favors the upper phase, obvious, right. If K is 1 less than 1, protein favors the bottom phase. Now, K remains constant over a wide range of polymer concentration, and this is how the phase diagram will look like. Polymer and A and salt, polymer B. Okay. So, we have polymer or salt here and polymer B here. So, this portion will remain biphasic and this portion will remain monophasic. Okay. So, we want to work at biphasic region here for the upper phase and this is for the lower phase. So, our goal is to work at biphasic so that after the extraction we can separate the phases actually, we do not want to work below this. So, this is called the critical point. Okay. So, we need to remember that. There are some terms which we need to remember. One is called the product yield or recovery in the upper phase. So, Y yield is equal to concentration in the upper phase, volume of the upper phase divided by concentration, total concentration containing original volume of V naught. So, if we modify this equation, this becomes Y equal to Vu, volume of the upper phase by volume of lower phase divided by volume of upper phase by volume of lower phase plus 1 by K. K is the partition coefficient. So, this is a useful relationship. So, if I know the partition coefficient, I can decide on what should be my ratio of Vu by Vl, what should be the volume of upper phase to lower phase to achieve certain yield. I want 90% yield, what should be the volume of upper phase and what should be the volume of lower phase, that sort of calculations I can do. So, the partitioning of two phases depends on interaction between the partitioned substance and the component of each phase. So, you have hydrogen bond, charge interaction, van der Waals forces, hydrophobic interaction, sterific effects, all these and the distribution of biomolecules depends on the molecular weight and chemical properties of the polymer, okay, how much interaction it is offering towards the biomolecule. So, what are the factors affecting partitioning? Polymer molecular mass, increase in molecular weight of polymer lowers the concentration. So, high molecular weight PEG has low coefficient factor, low molecular weight PEG reduces hydrophobicity. Better partitioning due to the low interfacial tension of low molecular weight. Partitioned proteins are attracted more to smaller sized polymers. A high molecular weight protein reduces free volume by increasing chain length, hence partitioning of biomolecules to bottom phase. Increase in polymer weight reduces the free volume of top phase, hence partitioning of molecules in salt rich bottom phase. Okay. Polymer concentration influences partitioning coefficient of proteins. High concentration reduces partition coefficient. High molecular weight and high polymer concentration have a negative effect on partitioning. So, if I use a high molecular weight protein and a high concentration, then it will not do good. High viscosity of the polymer reduces the space for proteins. Effect of salt, increase in salt concentration increases partition coefficient because it acts as a salting out. Negatively charged proteins partition to upper phase, whereas positively charged proteins to the bottom phase. Addition of salt to PEG increases the selectivity of the partitioning. Okay. Types of salt. Salt alters partitioning by changing the hydrophobicity of the two phases or partitioning of ions, right. So, polymer phosphate systems are generally used, Sometimes anionic salts are better than cationic salts for partitioning of biomolecules. Effect of pH. Partitioning of biomolecules also depends on the isoelectric point. It should be higher than the isoelectric point. pH of the system affects the charge of the protein and hence the partitioning. The phosphates used for pH above 7 and sulfate salt for pH below 6.5. So, if I am working at above 7, I will use phosphate. If it is below 6.5, I will use sulfate. Temperature. Preparation of phases is faster, but then you have to be very careful that it does not degrade your denature your protein. Surface properties of biomolecules. Net charge and amino acid composition of protein influence partitioning. More aromatic amino acids makes protein hydrophobic, so they will partition to polymer phase. Protein with lysine, glutamic acid, aspartic acid are less hydrophobic, so they will go to salt rich phase. So, you have to be careful what is the charge that is present on the protein surface properties. So, it is biocompatible environment, it is non-toxic, no solvents, high capacity, high yield, easy for scale up, can be operated in batch, low energy, practically low energy. What are the disadvantages? Low in selectivity, difficult in predicting the exact behavior, viscosity and slow segregation because both are water, difficulty in extracting, how do I re-extract. Then there are environmental issues because how do I dispose of the salt material. So, there are many examples of this actually, applications, examples, serine protease, IgG, luciferase, fireflies using PEG and phosphate, PEG magnesium sulfate, PEG phosphate, PEG rich with sodium ammonium sulfate and so on actually. So, extractive fermentation, we can combine fermentation with extraction in situ systems, PEG sulfate, PEG phosphate as you can see for a large number of antibiotics here. Cephalaxin, xylanase, asparginase, 6-phenyl for purone and so on actually. So, how do we do it? We can mix them together, that is batch process, we can mix them mixer and then phase separation, extract, raffinate, or we can have continuous system, continuous tubular. So, we have solvent, extract, feed, raffinate, cross current, counter current, you know all about it actually. So, let us look at two problems very important. Aqueous two phase extraction is used to extract xylanase from a solution, a PEG dextran system is used. The partition coefficient is 6. Calculate maximum possible enzyme recovery when the volume ratio of upper to lower phase is 4. Now, you need to use this equation, yield is equal to VU by VL divided by VU by VL plus 1 by K. Here yield is given as, no, the first part is K is given as 6, VU by VL is given as 4. So, I want to calculate yield. So, I put 4 plus 1 by 6 and I calculate Y, okay. And of course, the partition coefficient is greater than 1. So, it will partition to the upper phase, that you need to keep in mind. So, what do you get? 96%. So, with the ratio of upper to lower of 4, I am able to get 96% of the protein extracted if the partition coefficient is 6. Now, let us look at another problem. Enzyme is recovered using aqueous two phase. I am using 150 liters of homogenate initially, which contains 3 units of enzyme. PEG salt mixture is added to form two phases. Then the enzyme partition coefficient is 3.5. So, K is 3.5, yield is 80%. What is the volume ratio of upper to lower to achieve 80% yield? So, yield is 80%, K is 3.5. So, I take that equation, on the left hand side I know 0.8. So, I need to calculate VU by VL, it comes to 1.14. So, 1.143 if my ratio of VU by VL, I will get 80% recovery. Now, if the volume of the lower phase is 100 liter, okay, volume of the lower phase is 100 liter, that means VL is 100 liter. What is the concentration factor? 80% recovery, okay. So, VL is 100 liter, so VU I can calculate, okay. Then what is the concentration factor for 80% recovery, okay. What is concentration? You know Cu Vu plus Cl Vl is equal to C naught V naught, where is C naught is original concentration, total amount of total volume initially. So, C naught V naught gives you the total amount of solute. Now, the total amount of solute in the upper, total amount of solute in the lower, okay. So, and we know VL is 100, VU is 115 because we calculated VU by VL as 1.15. now Cu is equal to 3.5 Cl, okay. Therefore, I substitute here 3.5 Cl into 115 plus Cl into 100 is equal to 3.2 into 10 power 3 into 150. So, Cl is equal to so much and C is equal to so much, okay. That is concentration of the enzyme in the upper, concentration of enzyme in the lower, okay. So, concentration factor for 80% recovery, I will just do Cu by C naught, that becomes 1.04, that is Cu is this divided by C naught is given here, okay, 3.2. So, I get 1.04 value. So, you understand. So, we know we calculate VL from the first part, we know VU by VL is 1.15. So, we calculate VU. Now, Cu and Cl are related, okay, by this 3.5 into Cl, okay, because this is the enzyme partition coefficient is 3.5, okay. So, therefore, I substitute in this one. So, then I can get Cl and Cu, okay. Now, the concentration factor is Cu upper and C naught, okay. C naught is given as here 3.2 units. So, I substitute here, okay. So, I get a concentration factor of 1.04, that means that is the increase in the concentration of the enzyme when I extract it into the upper layer. So, it is a very useful problem to look at. It gives you an idea of what should be the ratio of the PEG for upper and the lower, and also it gives you an idea about the enhancement of the concentration after the extraction process. So, today we looked at two different techniques which uses aqueous. One is reverse micellar, where we use a surfactant, and the second one is called two phase aqueous, where we use a PEG like biopolymer. So, extraction in both the cases involves majorly water. Now, unlike the previous studies which we looked at where we use solvents. So, the advantage is we can extract proteins or enzymes without worrying about losing their activity. So, they have a lot of applications in bioprocess industry. Thank you very much.